Hi everyone. In this lecture we're going to be introducing the idea, the concept of a random variable. I will be denoting random variables as RVs because this is something that will be discussed quite extensively, so I'm not going to be writing random variables explicitly all the time. We are in the univariate case, so we're looking essentially a single random variable. This is going to change in the next lectures. We're going to move to the bivariate case where we're going to look at two random variables at the same time, and then the multivariate case where we're going to be looking at multiple random variables. The concepts that we are heading towards are the probability mass functions, for those of you who have some experience with probability and statistics from the past, which is the discrete case of random variables, and the probability density functions, or PDFs, which is the case for continuous random variables. So let's start with the definition. A random variable entails what we call a real valued function defined on the sample space S, which assigns a real number x of s lowercase to each outcome s lowercase that belongs in the set, in the sample space that we have called capital S. So that is essentially a random variable. So a few things to notice. A real valued function, right? So we are talking about functions. So there is some form of mapping that is happening. It entails values from the set of the real numbers. So essentially the assignment is of a real number to each of the outcomes in our sample space. Okay. This is going to become clearer as we're moving into some of the examples that we're going to be talking about, but that sort of is the essence of a random variable. So the mapping here goes from the S, which is a subset of the sample space capital S, and we map that into the space of real numbers. So essentially think about this as results of a variety of experiments, or possible results from a variety of experiments that you map into some form of a number in the space of real numbers. So we're going to start with an example here. Let's say the experiment that you're running is tossing a coin 3 times and letting x, the random variable, be the number of times that you have observed, let's say, heads. What are the possibilities in this particular example to observe heads once you toss a coin 3 times? You could have heads not appear at all. So you're tossing the coin and you're always getting tails. So that would be an outcome. You could represent that as T, T, T. So you get 3 tails. So no heads, that would essentially mean that for that particular outcome of the experiment, your x variable is going to take the value of 0 because you observed 0 heads. What is the possibility of observing 1 heads in the 3 coin tosses? Well, it could show up in the first coin toss, and then it might not happen again, so it could be tails, or it could be happening in the second toss. You would have tails, or it could be happening in the third toss. You would be having tails show up and then heads. So for these 3 potential outcomes of the experiment, you would be getting a value of x equal to 1. So going back to this idea of mapping, things that are happening as subsets of your sample space of all possible outcomes of the experiment, you are mapping those into a number that represents the outcome. So in this case, it's quite explicit. So what are the possibilities? So here are the possibilities. We've mentioned that you could be getting 0 heads, 1 heads, 2 coin tosses with heads, or all coin tosses arriving at heads, which would be an x equal to 3 because you're observing 3 heads in the coin toss. So that is something that we call a random variable. Of course, here on the right, you can see what the subset of your sample space is of capital S. In this case, it's the 3 tails and so on and so forth. You can feel free to fill out all of these possibilities. Eventually, you should have a sample space with 8 potential outcomes, and essentially then you can count how these subsets essentially relate to the numbers of the you assigned for the random variable. Let's look at a slightly different example that also involves an experiment where you toss coins. So let's say that you toss a coin repeatedly until you have heads appear. So you could be tossing a coin and getting heads, and the experiment stops. You could toss a coin and get tails, and then you toss it again and you get heads, and then the experiment ends. So you could represent the number of repetitions by defining a random variable. That would be random variable y. That would be the number of repetitions that you needed to observe heads. So it could be 1, it could be 2, it could be 3, and so on and so forth. Okay? So it becomes increasingly unlikely that you're going to be getting to a situation where you're going to have a high number in terms of materialization of your random variable here. But it is a theoretical possibility, so that's how we're going to sort of talk about this random variable. Other examples that do not relate directly to experiments that you can run with coins or with dice, which are very typical examples in mathematical statistics courses, or even cards, playing cards. We can move into sort of what we call the real world and what is going to be most relevant for us in econometrics. So a third example has to do with a different type of an experiment, right? So you randomly pick a university student. Okay, and then you define a random variable about this university student. It could be any characteristic that they have, but in particular in this example, let Z, capital Z, be the GPA that they're getting throughout in a semester. Okay, so from the situation of failing all of the classes that they're taking to actually getting a perfect GPA are all of these numeric sort of assignments that you can sort of make for this random variable that reflect some subsets of the sample space. In this particular case, it's harder to think about this because you're not necessarily running an experiment, but there are some features, there are some activities that will define essentially what the value of the GPA is. Another example of what could be a random variable is the following. So let's say you're considering the amount of time that it takes for a particular watch to break. You can name that random variable capital T, and that could be measuring the time in hours, in minutes, in years until that particular device breaks. The possibilities here could be is a continuous range. So T could be taking the values of 0. That would mean that the watch comes to you, you open it, and it's already broken, up to infinity. Theoretically, something like this could be running for a very long time. So now that we have the definition of a random variable and some examples of what a random variable is, we can introduce another concept that relates to random variables, and that is going to be the probability distribution of a random variable. Here, again, we're going to need an initial definition. We're going to say that for any subset of the real space, and let's call that subset, the probability that you're going to get a random variable value within that subset of the real space is defined as the probability of that particular subset of the sample space, such that the numeric values that you're getting that are mapped essentially from that subset of the sample space into the set of real numbers, those are your x's, belong in that subset A. It's a little bit of a sort of tough definition to sort of wrap your minds around, but some examples are going to be clarifying what that broad definition means in particular. So let's work with the example of the coin tosses. So we are going to say that we need to find the probability distribution for this random variable x such that x is the number of heads that are observed when we toss the coin 3 times. So we have already seen what are the possible outcomes for x. That would be 0, 1, 2, and 3. Now, what would be the probabilities that we can associate effectively with that particular outcome, right? So essentially what we're looking for is a probability assignment for all of these possible x's that we're going to be generating. Obviously, all of these possible x's relate to how frequent these subsets of the sample space are. So let's essentially explore that a little bit further. One of the first things that you can do is write down what is your sample space, if it's possible, if it's an experiment through which you can sort of enumerate all of the possibilities. For some experiments, this would not be feasible. So imagine if I change this problem into a coin toss 10 times, right? So it would be really tough to sit down and sort of write this out. We would be able to calculate, obviously, sort of all of these outcomes through other means, and in mathematical statistics you learn a lot about combinatorics, and there's other sort of areas that would help you do things like that. But in this case, we can enumerate the possibilities, right? So it ranges from getting all heads to getting all tails and everything in between. So you can systematically go through and sort of make sure that this captures all of the possibilities, all of the possible outcomes of that experiment. And when you have that information, what you can do is make a table. So on the first row, you can write all of the possible values that x can take, 0, 1, 2, 3. Underneath, you can start defining what is the probability that your random variable will take that particular value, either 0 or 1 or 2 or 3. Okay, and in order to do something like this, you can quite possibly go back into sort of the frequentist interpretation of probability and say, well, how many times out of the 8 possibilities do we get a situation where we are observing a 0 number of heads when we toss a coin 3 times? Well, we have 8 distinct possibilities in terms of the outcome of the experiment, and the only situation where we observe 0 heads is the case where we're getting the 3 tails in the coin toss. So 1 possibility out of 8, we can define the probability as 1 out of 8. Now, we can go to the situation where we are observing 1 heads coming up once in this experiment. Where do we see that? We see that in this particular outcome. We see that in tails, and we see that in heads. So these are 3 possibilities out of 8. So based on sort of our conceptualization, the frequentist conceptualization of probability, 3 out of 8. Similarly, we can finish up this table by looking at, well, how often do we see 2 heads in this 3 coin toss experiment? So we see that also 3 times out of the 8 distinct outcomes, so and this one. And then when do we see the sort of the materialization of the random variable taking the value of 3? Only when we observe the 3 heads in the 3 coin tosses. So that would be one case, 1 element of the sample space, 1 out of 8. So we developed the concept of the probability distribution for a random variable, and those probability distributions can be classified in 2 distinct types. The first case, or the first type that we're going to be talking about, are discrete probability distributions, discrete random variable probability distributions. The definition here is the following: a random variable x, typically you're going to be writing this as capital X, has a discrete distribution if it can take on only a finite or a countably infinite number of outcomes. A random variable that has a discrete distribution is said to be a discrete random variable. So we're going to be talking about discrete random variables and continuous random variables, and all of the things that we're going to be defining, all of the probability functions, the distribution functions that we'll see later on, will be specific to whether you're talking about a discrete random variable or a continuous random variable. So finite or countably infinite number of outcomes. So think again about coin tosses, think about dice rolls, think about experiments that might be involving cards. So we've seen some of these examples. So we're ready to define a concept that we're going to be referring to as the probability function of this discrete random variable. For these discrete variables, we call them probability mass functions, and in short, we're going to denote them as PF or as PMFs. So, given any discrete random variable with finite or countably infinite number of outcomes, we are going to define a function. We're going to use lowercase f to denote it, that we are going to call the probability mass function or the probability function. So PF or PMF respectively. Probability mass function of random variable x, such that for any x that belongs in the space of real numbers, the f of x is going to represent the probability that your random variable x takes a particular outcome. Let me repeat that. What is happening for this function? For any x that belongs in the space of real numbers, the f of x, the function, essentially, the function f, represents the probability that your x random variable is going to take a particular value. Again, we're going to continue on the previous example with the coin tosses, and we're going to simply write down what that probability function or the probability mass function is for this experiment. So there we're talking about the 3 coin tosses, the probability that x takes a specific value is simply this function that we call f of x, which is going to be equal to 1/8. If you remember from the table that we saw before, that was the situation where we did not observe any heads, or we had the 3 coin tosses that led to all heads, okay? And that probability was equal to 1/8. So 1/8 if x is equal to 0,3, right? So essentially give me the x if for this functional form, and f of 0 results to an 1/8, and the f of 3 results to a value of the f of x of 1/8. But also we had some distinct values, right? So the other 2 possibilities, the possibility of observing heads once or observing heads twice, the probability for that was equal to 3/8. So the f of 1 here is equal to 3/8, and the f of 2 here is equal to 3/8. So this is a compact way of writing this particular function, and that is essentially the probability mass function that emerges from the experiment that we run. Visually, you can see this in a diagram like this one. So you have all of the possible values of x on the horizontal axis, and you have the values of f of x on the vertical axis. So for the value of x equals to 0, you essentially get 1/8 for the f of x. For the value of x equals to 1, you get f of x, or the probability essentially of observing 1 at 3/8. Same thing for the value of x is equal to 2. And then again down to probability of 1/8 for the materialization of x at 3. Now, all of these probability mass functions, or whatever function can qualify as a probability mass function, is going to automatically be characterized by specific properties. And there is 2 of them, and I believe they are quite intuitive. So the first property of the probability mass function, this is simply an f of x, which is equal to the probability that your random variable is going to take on a specific value of x, has to be greater or equal to 0 for every x that belongs in the space of real numbers. That is for the domain, essentially, or specifically for the domain of your function, right? So for all of these values that x can take. Sometimes it's all of them. Sometimes they're going to be limited to a subset of the space of real numbers. The main message here is this f of x is non-negative. Okay, so rather simple property, and all of the functions that can qualify to be probability mass functions need to follow that particular property. The second property has to do with the summation of all of the values of the f of x. remember that we were getting a value for f of x for each of the discrete outcomes that we were getting. So we had one f of x value, the f of 0, the f of 1, the f of 2, and the f of 3 for the previous example that we were working with. So when you sum all of these f values up, remember these are probabilities, right? The f is a probability. So if you sum them all up for all of the possible x's, that summation essentially needs to be equal to 1, because you're adding all of the probabilities of the different outcomes that you could be observing, and sort of intuitively thinking about this intuitively, you cannot get a probability of more than 100%, right? So in this particular situation, we're representing that probability as equal to 1. So the sum of the f of x is essentially the sum of all of the probabilities that you could be observing any of the possible materializations of your random variable. Note that particularly for probability mass function, that f of x value is going to be less or equal to 1 for every x in the space of real numbers, or for all of the possible outcomes for your random variable. So all of these values f of x reflect probabilities, and naturally probability ranges between 0 and 1, so that's why we need to impose that constraint here, and that applies only for the probability mass function. This is going to change when we talk about the continuous case. The second thing that you can note about these properties is that for any subset A in the space of real numbers, the probability that your x values belong in that subset is simply the sum of your f of x's where the x falls within that subset. So all of this is saying is that if you want to add up probabilities for any specific values of f of x and get sort of the probability of, well, what is the probability that we're either going to observe, let's say, 0 heads or 1 heads in this experiment, you can simply take those f of x values and add them up, right? So if you sum up f of x0 and f of 0 and f of 1, essentially you're getting a probability that you could be observing either of these two outcomes. So what this example is saying here, what is the probability, for example, in the experiment that we have been using as an example of the three coin toss, that your random variable is going to take a value of less or equal to 1. The possibilities here that it's either going to be 0 or it's going to be 1. Right? So how do you calculate that? Well, what is the probability that you don't get any heads in the 3 coin toss? What is the probability that you're going to get only 1 heads outcome in this sequence of coin tosses? So 1 over 8 plus 3 over 8, that typically makes 4 over 8, which is 1/2. So that would be a 50% probability of observing your random variable outcomes being essentially less than 1. So these are the properties for the case of the discrete random variables. The other classification of random variables involves continuous random variables, and the definition here is as follows. A random variable capital X has a continuous distribution if there exists a non-negative function f on R. So now this idea of a non-negative function should be becoming a little bit clearer, such that for a particular interval, and let's call that interval, it could be an interval something like between 2 and 4. It's sort of a range of values. The probability that your random variable falls in that interval is equal to an integral over the interval. Okay, again, the integral over the interval that we have defined of that function f of x dx. So this is again a non-negative function defined in the space of real numbers. That's the domain for x, where you integrate that over a particular interval, and then you arrive at the probability that your random variable x falls in that interval. So it does change a little bit in the continuous case, in the sense that we're not talking about a specific materialization of a number here. We're talking about x belonging in a particular interval of values, and we'll see why this happens in a little bit. But the idea also here is similar in terms of summing up f of x values. We're using integration instead of summation sign because we're in a continuous case, but sort of the analogy is quite strong. So the f function here we're going to refer to as the probability density function, and from now on I'm going to be talking a lot about PDFs. That means probability density function of x. So essentially what this says is that once you have a probability density function, you can extract information about probabilities that your random variable takes a specific set of values by using an integration technique over that functional form. So a random variable x with a continuous distribution is said to be a continuous random variable, and hopefully that makes sense for everyone by now. So one thing to note about continuous random variables and their probability density functions, those f functions, is that since they are greater or equal than 0 on the basis of their property, they're non-negative essentially, if you integrate over those functions, essentially what you're getting as an outcome is the area underneath those curves, whether they're straight lines or whether there's some nonlinearity. Essentially, the integration over an interval means that you're calculating what the area underneath the curve is. That's going back to your basic knowledge of integration. And what we're going to realize is that this area, what is going to be giving us the probability value of your random variable belonging in that particular integral. So the idea that you integrate over an interval signifies that you're calculating essentially the probability that your random variable takes values within that interval, which is very important to understand that essentially the height of this function f does not give you probability. In the case of discrete random variables, where if you remember your probability mass functions, the height, essentially those points that we were calculating, the 1/8 value of the f of x for x is equal to 0, the 3/8 value for the f of x when x was equal to 1, those were interpretable as probabilities, but those were specific values of x. Here we're talking about intervals, a grouping of values of x, and you're not getting the probability from the height, essentially, of your functional form. You're getting the probability by integrating over an interval. So, visually, this could be your f of x. This would be sort of an integral, so x goes from this value, this lower value, to this higher value. All of the area underneath your curve is going to be a number, and that's going to denote your probability value for your x falling within that particular interval. So remember the contrast here with discrete random variables. The probability that x takes a specific value of x is found from this functional form, right? But this is not the case for the continuous version of this concept. So let's talk a little bit about the properties of the probability density functions. In the continuous case, they are exactly the same as the properties for the discrete case. F of x is non-negative for every x in the space of real numbers, or a subset, depending on how this f of x is defined, what is the domain of x. So that relates to the fact that you can calculate an area under the curve, because this is a non-negative sort of function. And then the second property has to do with what happens if you let that interval range for the full possible set of values, right? So if you let x go to minus infinity or x go to positive infinity, and you integrate this f of the x, what is the value that you should be getting? And that has to be equal to 1. So this is a powerful concept, because you can think about any functional form that you have studied so far. If it fits this definition, right? If that functional form is non-negative, and if you integrate it for all possible values of x, it takes the value of 1, you can use this functional form as a probability density function. Different phenomena that we observe in economic systems, in social systems, in the natural world are described by probability density functions, right? And the multiplicity of functions that we have available that potentially can be described by these two properties give us a lot of theoretical possibilities about how things are sort of distributed probabilistically. So the area underneath the curve has to be equal to 1 as x ranges from -infinity to infinity, and these f functions need to be non-negative. See, these are the two basic properties. Note that this f function is a PDF even only if it satisfies these two properties. So that's something that you need to check in many ways as you're exploring the possibility that you do have a probability density function in your hands.